Hello, students. So, we're going to start with defining potential energy very carefully in this video, and then we're going to get to the whole point, which is defining the mechanical energy of an object and why that's useful. So, this potential energy, let's take an object that's falling. So, this is going to be the gravitational. That's important because there are other potential energies. So we'll take a falling object, and it starts at some initial point and goes to some final point. So I've drawn in delta x here, and it'll have some initial velocity and some final velocity, and it'll have some mass, and it's going to be a falling object. So the weight force is going to be the mass times the gravitational acceleration, which is going to be minus m times g, which we usually just specify as 9.8 times our vector. So up is going to be plus j hat, and across is going to be plus I hat. All right. And then our displacement is going to be x final minus x initial, and that's going to be in the j hat direction. So when we do the work that the weight force does, that's going to be minus mg x final minus x initial. All right, because what we're doing is we're dotting these together. All right. And so so what we get is an expression that it's mg x initial minus mg x final, like that, where that minus sign changes this around. So that's the work it's done. Now, it makes more sense to leave it to look like this up here. And what we're going to do is define our potential energy as mgh. Or what we'll do is we'll say x final is h final and x initial is h initial. So our change in potential energy is going to be mg, well, there's going to be a minus sign, h final minus mg h initial. All right, that's just saying this again. And this is the work. Oh, I want to be careful. Scrub that out. So our change in our potential energy is going to be defined by final minus initial. It's going to be mg h final minus mg h initial, which is minus the work that the weight force does. Right? So there's a reason why we're being very careful in labeling this all out. Now over here off to the side, I just want to point out that when this thing falls down, change in kinetic energy. Right? We can define delta K. But that is because there's only one force acting on this. That is the work that the weight force does. So for a falling object, the change in the kinetic energy looks like minus the change in the potential energy. All right? That's kind of an important thing we're going to get to. So we've defined our potential energy, and we've defined it carefully in such a way that things will start to make sense in a moment. So we can ask, what if there's other forces acting on these objects? Right? Well, maybe they're forces that we can define a potential energy for. Maybe they're not. The notes, in particular, kind of discuss a little bit of what's going on with conservative forces, I think. Somewhere you should have that. Certainly the textbook talks about conservative and non-conservative forces. But the point is that certain forces we can define potential energies for, and those are the ones where we don't care the path that the object takes. So I'll do an example for you here in a second, talking about that. But the gist of what I want to get to is if what we have delta K minus delta U here, sorry, plus delta U, that is the kinetic energy plus the potential energy. That is effectively, we're looking at delta K is the net work, and we're subtracting off the work that the gravitational force does, the weight force. So this is all the external forces. This is also what we call the non-conservative. Right? So we can actually write out these terms. All right, we can do K final minus K initial plus U final minus U initial on that side. And we can group these. K final plus U final, and then plus minus K initial minus U initial. And we'll pull out a common minus sign here. And what we note, we can define a thing here, the energy is K plus U at a particular location. Right? And so what we have here is E final minus E initial. The mechanical energy, the difference in mechanical energy is whatever the external forces are doing. Right? So what we're talking about is the mechanical energy and so far the mechanical energy is it's the kinetic energy plus the gravitational potential energy. So it's 1/2 mv squared plus mgh. So if you're reading the lecture, if you're reading the textbook, those chapters 7 and 8 are talking about springs as well. And there is a spring potential energy. You can read those. We'll go over it when we talk about springs. But there's other forms of energy, and we're going to extend this as we go along. When we talk about rotating objects, there'll be a rotational kinetic energy. When we talk about springs, there'll be a spring potential energy. When we talk about other types of forces like electricity and magnetism, there can be potential energies for those. The idea is that this is the mechanical energy. So this gets to the bit, well, what if the external work? What if the other forces do no work? That's what we get. This is that the total mechanical energy does not change. So I want to do an example problem. In your notes, you'll have some examples. There's one for the potential energy, which I'll do at the end of this video, let's say. But I want to do the problem where there's the roller coaster. So there's a roller coaster, and we'll start up here. And so we'll put in a datum down here. This is going to be our y equals 0. This point is y is 60 meters. And we're going to make it do the loop-de-loop. And this point up here will be our Y is 20 meters. And we're going to use a 500 kilogram roller coaster train. And we're going to start it at V is 0. I'll start it at rest at the top of this ride, and we're going to go through the loop-de-loop. So what we want to know is, what is the velocity there? And then we also want to know what is the velocity here. Now this is a problem where I've given you nothing about slope of any of these bits. In fact, they curve. There's nothing in here that allows you to use forces cleanly. So what we're going to do is attack this using mechanical energy. I want to ask what the energy is here. Well, it's 1/2 mv squared plus mgh. And this term is 0 because the velocity is 0. So it's just mgh is 500 kilograms times 10 meters per second squared. Check to see this actually ending up on video. Good. Times 60 meters. So I have 1, 2, 3, 4 zeros. And 5 times 6 is 30. So it's 300,000. Kilogram meter per second squared is a newton, times a meter is a joule. 1 joule is 1 newton meter is 1 kilogram meter per second squared. Sorry, meter squared per second squared. And all the different versions of this that you've seen for kinetic energy and potential energy and work all have the same units. But anyway, this is our energy. This is our EI. So now down here, which I'll go ahead and I'll do in red. If there's no friction and there's no air resistance, then we can go and say, well, the energy is conserved going through this loop. So we can ask the velocity here. Well, that goes, what is E final? It is just 1/2 mv final squared plus mgh final. And now this term is 0. And E final has to be E initial. So we'll have 300,000 joules is 1/2 500 kilograms times V final squared. So we'll bring in the calculator. We'll pull the 2 over. So that's the 600,000. And we'll divide by 500. And then we'll take a square root. And we get V is 34.6 meters per second. And it's just that easy. So now we need to find at this new point up here what is, and we do the same sort of thing. We started here. When we get to 20 meters, what we've done is now we have this expression. E final is E initial. E final is just 1/2 mv final squared plus mgh final. And E initial is 300,000 joules. So now we have to account for both of these. Both of these are not, no, neither one of these is 0. So we'll have 1/2 500 kilograms. V final squared is 300,000 joules minus 500 kilograms times 10 meters per second squared times 20 meters. And so we can solve for V final. V final squared is this 300,000 joules times 2 divided by 500 kilograms. And we do the same thing over here. Minus 2 times 10 meters per second squared times 20 meters. I'm going to run out of paper. But generally, this is the answer. We're just doing the calculation now. So, all right, this left term is 1,200 meters squared per second squared, and then the right term is 2 times 10 times 20. 400 meters squared per second squared. And so V final is the square root of this, which is 28.3 meters per second. So this is the process by which you would go through a problem. And so what I want to do is clean sheet of paper, go through that process. So right. So for conservation of energy, you're going to do E final is E initial. And you're going to say what those are on each side. 1/2 m V final squared plus mg H final is 1/2 m V initial squared plus mg H initial. And then you identify in the problem anything that might be 0. And generally, one side of this equation you will know, and the other side will have the variable you want to solve for. And so when we did it here, at this point, we knew H is 0. And at this point, we knew H was 20 meters. And we knew everything up here, right? Because we knew this and that. And so we can solve, we can get our initial energy, and we can use it to find our final energy. So in the next video, because this is going on long enough, we'll do problems where we say, well, what if we have to include friction? Because we didn't include friction here, and we didn't include air resistance. But what happens if there's an external force? Not gravity, nothing with a potential energy. Well, what we'll do is say, well, the external work is the final energy minus the initial energy. So we'll have to figure out what those are. So that's going to be in the next video. Now, I do want to go back because I said I would do this problem of an apple falling out of a tree. So, tree, apple falls. This distance is 3.4 meters, and the mass is 75 grams, 0.075 kilograms. So first, we're going to say what is the work that the weight force does. What's the change? It's the minus change in potential energy. And so that's going to be mg delta x or delta y is going to be 0.075 kilograms times 10 meters per second squared times 3.4 meters. All right, so 0.075 times 10 times 3.4 is 2.55 joules. And that is the inverse of the change in potential energy. So what that means is, in terms of this picture that I'm drawing here, which is everything sliding off the page, sorry about that, we can say this point represents the gravitational energy is 0. And at this point, the gravitational energy is 2.55 joules. And so when the weight force does the work of pulling this down, we lose that potential energy. So we can go back and say, well, what is the speed of the object? What is v here? Well, that's going to be based on the change in kinetic energy, right? And the kinetic energy changing should be the inverse of the potential energy, which is just the work that the weight force does. This is just applying the weight kinetic energy theorem. Right? So we can just say delta K is 2.55 joules. But apple falls starting from rest, so V is 0 there. So this is just 1/2 m V final squared is 2.55 joules. And so V final is big square root 2 times 2.55 joules over 0.075 kilograms. Now, this is showing you how to work with it. Obviously, you could start from these 2 points in this distance and gravity with kinematics and get the same answer. And what we get is 8.24 meters per second, or 8.25. I round poorly at the end of videos. So let's stop here and upload this, and we'll get to what happens with external forces.